Hello everyone and welcome to A+ Physics. I'm Dan Fullerton and today we're going to do something a little bit different. What we're going to do is we're going to take the 2015 AP Physics C Electricity and Magnetism exam, look at the free response questions that they have on that one. So we'll go through free response questions number 1, number 2, and number 3 in sequential order. Now, as we do this, please keep in mind as I'm making this, they have not released the full solutions to the exam yet. So it's possible I make a small mistake here or there. Definitely within the realm of possibility. I make mistakes all the time. But this should at least be a good guide as to how I might go about attacking some of those problems. So with that, why don't we take a look at question number 1. All right. Question 1 starts by talking about a parallel plate capacitor with 2 parallel metal plates, each with area A. So let's draw a quick diagram of these. And we have a charge plus Q on the top one and minus Q on the bottom one, and they're separated by some distance here, D. All right, as I look at that question, first thing it asks is to draw an arrow to indicate the direction of the electric field between the plates. All right, that one's pretty straightforward. Electric field's going to go from positive to negative. So there's our electric field line, our arrow. And also draw an appropriate Gaussian surface that will be used to derive the expression of the magnitude of the electric field between the plates. And there are lots of different ways you could do that. But the way that I'm most comfortable with, that I typically do, is I like the cylinder. So let's draw a cylinder that goes through that top plate just like that, so that we have this bottom plate that's in the region between those two. And that should work for a Gaussian field there. Now, or for a Gaussian surface, excuse me. Now, for part A3, it says, using Gauss's law and the Gaussian surface from part A, we're going to derive an expression for the magnitude of the electric field. All right, so just an application of Gauss's law. Let's go to that then. The integral over the closed surface E dot dA is equal to the total charge enclosed by that surface divided by our constant epsilon naught. All right, well, as I look at this, because I've set up my Gaussian surface so carefully, the electric field at any point where we're not on the sides, or we're not going to have those cancel out, well, it's going to be constant. So I will have electric field integral over the closed surface of dA. That's just going to be the area A. So the left-hand side becomes the area, where we're looking at this as our area, is equal to the enclosed charge. Well, to find the enclosed charge, that's a little bit trickier, but not too bad. If we have plus Q over some area A, I'm going to define a surface charge density, sigma, which is that charge divided by the area of the plate A. We'll need to be careful of which A we're talking about. This is the area on the bottom of our cylindrical surface. This is the area of our plates, but I think we can keep it straight here using those same terms. Or, since this is Q over A with whatever charge is enclosed, when we write our enclosed charge, that's just going to be our surface charge density, sigma, times the area that's enclosed by our surface A, which is the same as that A, divided by epsilon naught. So, looks like we can divide the A out of both sides, and I come up with an electric field now that is sigma over epsilon naught. But we just said sigma was Q over our total area, our surface charge density. So that becomes sigma equals Q over A, so epsilon naught A. So for our final answer here, the electric field between the plates, defined at that surface, is just going to be Q over epsilon naught A. Quick application of Gauss's law. And if you were doing this on the test, you might want to go in a little bit more or less detail depending on the speed you go through these. I'm going to try and go through these fairly fast. If you want more information on how to apply Gauss's law, things like that, go back to the previous lectures on those specific topics. All right, so now we start getting a little bit tricky in this problem, getting a little funky. It says the space between the plates is filled with a dielectric material that's not a constant dielectric. the dielectric constant changes as you go from one plate to the other. And as a result, it tells you that the electric field then is given by this formula, minus Q over epsilon naught kappa naught e to the minus x over d times the area, all in the direction of the unit vector I hat. And it looks like we're defining this as our plus x direction. And it tells us kappa naught is a positive constant. So what we're asked to do now is find an expression for the dielectric constant kappa as a function of x. All right, that's kind of an interesting question, sort of thing you don't usually see. But if I were doing this, I would try and find the form where this looks a little bit more familiar and see how that kappa fits in. So when I did this, I started out by looking at the electric field between two parallel plates as V over D. All right, but if that's the case, well, V is Q over C for a capacitor, so that will be Q over CD. All right, but the capacitance is epsilon naught A over D for a parallel plate capacitor, so that will be QD over kappa epsilon naught AD. Our distances between the plates will cancel out, and I would get something that looks like Q over epsilon naught kappa A would be what I would typically get for an electric field for a standard constant dielectric capacitor between them. That's pretty close to this formula. The only thing I see that's different, if I analyze here, we've got A and A, we've got epsilon naught and epsilon naught. Instead of kappa, I now have this expression. So that would tell me that kappa is equal to kappa naught e to the minus x over d. So that's what I would answer for part B, that kappa is equal to kappa naught e to the minus x over d. And now we've expressed that as a function of x. So now the next part of the question asks us to write, but do not solve, an equation that could be used to determine the potential difference between the plates of the capacitor. Well, the way I would do that, since they give us the electric field, I would note that the potential difference, delta V, that's the opposite of the integral of E dot dl. Or in this case, that'll be the opposite of the integral from x equals 0 to that final value d of our electric field equation, which they gave us up here, minus q over epsilon naught kappa naught e to the minus x over d a. And as we dot that in the dl direction with I hat, that's just going to be our dx. So that's what I would put down for part C1. That would be the equation that we could solve. And for part C2, it asks us to derive this potential difference, where delta V is Vd minus V0. So now we've actually got to go and solve this piece. All right, so what we would do next here, let's see, I would pull the constants out of our integral. So that would be equal to, we've got a negative and a negative, so we'll end up with a positive. Q is constant. We have epsilon naught kappa naught a here, integral from x equals 0 to d, and what we're left with here is e to the x over d dx. And that fits the form e to the u du, except our du has to have 1 over d. So I would need a 1 over d here in order to make that work. If I put a 1 over d here so I fit the form e to the u du, I need to put a d over here, so we're really just multiplying by 1. So at that point, I've got something that I can actually go and integrate. And I'm going to finish that here on a new screen because I think we're going to run out of room here pretty quickly. So let's flip to the next screen to finish that integral. All right, so what we have then is delta V then will equal, we've got our constants, QD over epsilon naught kappa naught A, and they have the integral of e to the u du, which is going to be e to the x over d, and we're evaluating that from 0 to d. All right, write our constants again, QD over epsilon naught kappa naught A Now what we're going to do is substitute in e to the x over d, where that's going to be e to the d over d, or e to the 1, which is just e, minus e to the 0, which becomes 1. Therefore, I would write that delta v here, vd minus v naught, will be qd over epsilon naught, kappa naught, times our area, times the quantity E minus 1. And there we have our formula for potential difference. All right, now for part D, it says determine the capacitance of the capacitor. Well, at this point, we've done the hard work, so for part D, capacitance is just charge divided by voltage. Well, our charge, Q, is pretty easy. Divided by voltage, we just put in our equation for voltage, so Q over V, that'll be Q epsilon naught kappa naught A, divided by QD E minus 1. And a nice little simplification here, I have charge on both sides, and we would expect charge to make a ratio of 1 to not be in our final equation. So I would write this as epsilon naught kappa naught A over D E minus 1. It's interesting to note how similar that looks to our standard capacitor equation. C equals kappa epsilon naught A over D. The only difference now that we have is instead of kappa, we've got our kappa naught and the function E minus 1 down in the denominator. All right, so now we move on to part E. It says the energy stored in the capacitor that has a varying dielectric we'll call UV. The second capacitor that has a constant value, K naught, is given the same charge. Its energy stored is UC. How do the values of those compare? Well, the way I would do that is I would look at each of these and find out what their potential energy stored in is for the given conditions. So for the varying capacitor, varying dielectric, well, U in a capacitor, the stored potential energy is 1/2 CV squared, which we can replace Q with Q over C to write this as Q squared over 2C, which, as we finish this up, Q squared over 2, and we just figured out that C is epsilon naught kappa naught A over D E minus 1. There, that's a little better. So that's what I would come up with for the potential energy stored in that one. If, however, we had a constant dielectric constant in our capacitor, so if we have constant kappa, we can use our same formula, U equals Q squared over 2C, which is going to be Q squared over 2, the capacitance of a standard parallel plate capacitor with the constant dielectric, epsilon naught kappa naught A over D. So as I now compare these two, I notice that the only difference is this factor E minus 1. And since this E minus 1 factor, E minus 1 is greater than 1, that means this one must be bigger, so the potential energy stored in our new capacitor is greater than that stored in our standard capacitor. All right, I think that finishes out number 1. Let's take a quick break and we'll come back and we'll look at number 2. All right, we are back with free response question number 2 here. In this case, what we're given is a simple circuit that has a real battery instead of an ideal battery, along with a variable resistor and a voltmeter that we put across that variable resistor in parallel, of course. So the first thing we're asked to do is derive an expression for the measured voltage V. Well, I would use Kirchhoff's voltage law, KVL, and as I go around here, I would start at the bottom right and make a clockwise loop. And I see the negative potential, the negative EMF of our battery, plus our current flow through our internal resistance of our battery, IR, plus the voltage measured across our voltmeter, which will be I times our variable resistance by Ohm's law. And then we come back to where we start, so all of that must equal 0. Therefore, as I'm solving for V, V equals E minus IR, but I equals V over R by Ohm's law, so this becomes E minus ER over our total resistance, R plus R, or I could write this just by factoring out the EMF as E times 1 minus R over capital R plus little r. And there are several other ways you can derive that fairly quickly. That's just my quick approximation there. All right, so now for part 2, it says rewrite your expression from A to express 1 over V as a function of 1 over R. Looks like we're probably getting ready to graph something. So we've got to go adjust this to make this fit the form that's going to fit a line a whole lot better, a y equals mx plus b form. So some algebraic manipulation probably going to have to occur. So the first thing I'm going to do is I'm going to look at my equation over here. I've got V equals E minus IR, or V equals E times the quantity 1 minus R over R plus R. I'm going to go back to this version and just write, to begin with, I'm just going to invert both sides. 1 over V must equal 1 over E minus ER over R plus R. Inverting that side and that side. So now I've got the 1 over V, but I've got some work to do over here. All right, as I look at that then, I can multiply that by R plus R over here, multiply that by R plus R, that by R plus R, that by R plus R, just distributing this out, putting it in a slightly more useful format, I hope. So as we look over here, this will be R plus R divided by E times R plus R minus ER. Slightly more manageable, but still not overly pretty. Well, what I can do now is I can multiply through my EMF times our big R and little r. So that will equal capital R plus R divided by ER plus E little r minus E little r. And that's kind of nice. ER minus ER, well, that'll make 0, so we can get rid of that in the denominator. So now I have capital R plus little r over EMF times capital R. Okay, well, we've got this in the form of one fraction. Let's split it up, R over ER plus little r over ER. So that will be capital R plus ER plus R over ER. Okay, so now if I go another step further, this is still all equal to 1 over V equal to, well, this is 1 over our EMF, 1 over E plus R over ER. Or if I rewrite this once more, 1 over V equals, and I'm just going to switch the order of these. On this side over here, R over ER, I'm going to write as R over E times 1 over R plus, and I still have this 1 over E term. And why I wrote it that way is now I have this in a form y equals some constant m, our x 1 over r plus b. So I'm fitting it to the form of a line. Our 1 over v would go on our y-axis, r over e would be our slope, 1 over r would go on would be our x-axis, and 1 over e would be our y-intercept. So we've done that. We've written 1 over v as a function of 1 over r. So that would cover part A2. A little bit of algebra there more than physics, but something you can get through. Now, for part B, it says, on the grid below, plot data points for the graph of 1 over v as a function of 1 over r. Clearly scale and label all axes, of course, including appropriate units, and then draw a straight line that best fits the data. So your best fit line. All right, so I drew our axes in here. Now what we're going to do is plot our data. So I'm going to have 1 over r on this scale, which will be in units of 1 over ohms. And we'll have 0, 1, 2, and so on. And on our y-axis, 1 over our potential in 1 over volts. And we'll have that go at 0.1, 0.2, so it'll be 0.15, 0.05, 1 over volt increments. Then we just plot our data here. It looks like we've got for a potential of about 0.18. Somewhere in here we have for a resistance of 2, we've got a potential of about 0.18. So somewhere in there for about 0.135, we've got 1 over r. Well, for 1 over r of 1, we've got 0.135. For, let's see, 0.5, we have 0.106, somewhere around there. And keep doing that, and I will put one more point in here. Of course, you would put all of them in here. 1 over r of 0.1, we're at about 0.088. So we get something kind of like that, and there'll be a couple more points in there. Take your time, plot the points very carefully. Then draw your best fit line. All right, as I draw a best fit line, mine will look something like this. Again, I didn't draw it nearly as carefully as you guys would. But there's my best fit line. And while I've got that up here, pretty certain I'm going to need the slope here. Oh, and it's going to tell us in a minute to go and find the EMF and the internal resistance. So I'm going to find the slope while I'm here. And I'm going to be very careful not to pick data points specifically, but points that are on my best fit line. And I think it's usually a good idea to circle the points you're using. So when I did this for real, I had a point that was pretty convenient to use that was right over here, and one fairly far away. I think I used the y-intercept there. So when I did my slope came out to be about 0.19 y2 minus y1, 0.08 over 2.3 minus 0, or about 0.0478 ohms per volt. All right, so now for part C, it says use that straight line part to find the EMF and the internal resistance. Well, we know that the slope is going to be useful and the y-intercept because we just did that in the previous problem. The EMF is going to be 1 over the y-intercept from our previous work. So I just look over here to what my y-intercept is, which was 0.08 1 over volts. So my EMF is, oops, let's fix that up there. My EMF is 1 over 0.08 1 over volts, or 12.5 volts. And your data may be slightly different depending on how you drew your graph, but you should be in that ballpark. The internal resistance then is the EMF times the slope. So that's going to be our 12.5 volts times the slope we just determined, 0.0478 ohms per volt, where I came up with about 0.598 ohms. Again, all this comes from our previous work where we determined how that function fit the form of line. There we go. All right, now for part D of the experiment, it says using these results, find the maximum current the battery can provide. Well, to find the maximum current, I'm going to go back to Ohm's law again. Maximum current is just E over R, where our EMF is 12.5 volts. And the maximum current occurs when you have the minimum resistance. That's going to occur when the only resistance in the circuit is that internal resistance of the battery, or 0.598 ohms, to give me about 20.9 amps, if I'm reading that correctly. All right. One more here. Let's go to the next page to give ourselves a little bit of room. A voltmeter is to be used to determine the EMF of the battery after removing the battery from the circuit. 2 voltmeters are available, one with low internal resistance, one with high internal resistance, which will provide the most accurate measurement. Well, now, of course, you want the voltmeter with high resistance. You want a voltmeter to have a negligible effect on the circuit. That means you want it to have a very high resistance, drawing the least possible amount of current so that it causes the smallest potential drop in the circuit and you get a more accurate reading of what's going on. To justify that answer, I would say something like, well, we know V equals E minus IR. We want that high resistance to minimize current and voltage drop due to the internal resistance R of the battery so that the voltmeter most closely reads the EMF of the battery. So find some way to put that into words, a sentence or two, and you should be good with justifying your answer here. And that finishes up E&M number 2. All right, we'll take another quick break, and we'll come back to do number 3. All right, one more problem to do here. It looks like this time we've got a circular wire loop in a magnetic field, so probably looking at an induction problem. The magnetic field in the direction shown is given as a function of time, where the magnetic field as a function of time is equal to A, some constant, times 1 minus BT, where B is also a constant. It gives us those constants. It also says that we are in a magnetic field where compared to the loop, there's our loop, the magnetic field is coming out this direction, and that angle is 60 degrees. Interesting. Typically when we look at these angles, I like analyzing the one that's between those two. So we're going to have to keep in mind which angle we're using very carefully as we go through our calculations. Might be more useful to say this one's 30 degrees down here. All right, so first thing it asks us in this problem, part A, derive an expression for the magnetic flux through the loop. All right, well, the magnetic flux through the loop, that's just going to be the magnetic field times the area. So it looks like we're going to have, we've got our magnetic field strength, so we'll have that in there, A times 1 minus BT. All right, we need to have the area of our loop. That's going to be pi r squared. I can just write that as area for now. And then we also have to have the factor from this angle. It's not all going directly through the loop. And I'm going to go back to my more familiar way of doing this and measuring this angle, calling that 30 degrees. So I'm going to throw in the factor of sine 30 degrees there. Or you could have used cosine 60 degrees, get the same value depending on how you're looking at the problem. So just expanding this out with what we know, that's going to be 4 times 1 minus 0.2t times the sine of 30 degrees times the area of our loop. It's a circle, so that's going to be pi r squared, pi times 0.1 meter squared, or 0.0628 times 1 minus 0.2t. And there we've got to start on the problem. All right, for part B now, it says calculate the numerical value of the induced EMF. All right, the EMF is just going to be the opposite of the time rate of change of the magnetic flux, the derivative of the magnetic flux with respect to time, which is going to be the opposite of the derivative with respect to time, and I just plug in my formula here that I just derived for the magnetic flux, 0.0628 times 1 minus 0.2t. All right, as I take the derivative of that, 0.0628 times 1, that's just going to be a constant. Derivative of constant is 0, so all I have to worry about is the 0.0628 times 0.2t, which is times a single variable. The derivative of just a dt is going to be 1, so all we have is 0.0628 times 0.2, and our negatives are going to make a ratio of 1. So I take the derivative of that, and I come up with 0.0126 volts. Again, I'm walking through these fairly quickly as far as the math goes. Feel free to stop, take your time, make sure that I'm not making any mistakes here. Like I said, I haven't checked these with anything. All right, part C. Calculate the numerical value of the induced current in the loop. All right, well, we've got our potential, and it gives us the resistance. We can just use Ohm's law. I equals our potential difference divided by our resistance, which is going to be 0.0126 volts, divided by our 50 ohms, where I come up with 252 microamps. Very good. What is the direction of the induced current in the loop as viewed from point P? Well, if we look as a function of time, as time gets bigger, it looks like our flux is getting smaller. So the induced current is going to create a magnetic field that would want to oppose that change by Lenz's law. So if it wants to oppose that change and it's getting smaller, it's going to come up with a direction that's going to create an induced magnetic field that's going to keep it going through the loop. So by the right-hand rule, as I point my thumb in the direction of the B field in order to try and maintain that, my fingers wrap around that in a counterclockwise direction. So I will call that counterclockwise. It's always difficult and challenging to explain how you're using Lenz's law to come up with the direction of these. But do your best to put this in words. Something like the flux through the loop is decreasing, the induced current opposes that change, resulting in a counterclockwise flow by Lenz's law or the right-hand rule. Some way where you try and verbalize that or put that down on the written page to justify your answer. Those are always a little bit challenging. All right, let's give ourselves some more room on another page here to go finish off this problem. Assuming the loop stays in its current position, find the energy dissipated in 4 seconds. Well, the way I would do that, the energy dissipated in 4 seconds, that's going to be the power times the time. So electrical energy, W, is power times time, where our power we can find just from V squared over R times our time of 4 seconds. So we have 0.0126 volts squared divided by our 50 ohms times 4 seconds. Or I end up with about 1.27 times 10 to the minus 5 joules. Okay, one last part. Indicate whether the net magnetic force and net magnetic torque on the loop are zero or non-zero while the loop is in the magnetic field. And this is going to be a really tough one to explain in a video without you just looking at it and trying to visualize, because it requires some three-dimensional thinking. But the net magnetic force I come up with is going to be zero. All the forces you have on one side pointing up correspond with those going down on the other side. Everything balances out. You get a net force of zero, even though there are forces over individual parts of that wire. However, the net torque is not. I would say the net torque, I'm not sure equals is the right criteria there, but it is non-zero. The net force in the loop on the loop is zero as all the forces cancel out. The net torques, however, lead to a rotation of the loop about an axis of rotation through its center. So when I look at this and visualize it, I get a net torque that's non-zero. All right, hopefully that gets you a good feeling for the E&M test from AP Physics C in 2015. Thanks so much for your time, everyone, and make it a great day.